So let's begin with the event. And before we start, I think it's a very good occasion that we have. And right now, I'd like to introduce Dr. Supratim Mitra, who would be sessioning the chair. He is an assistant professor at Vanasthali Vidyapit Department of Physical Sciences, which has more than 17,000 students on campus, and is actually the world's second largest residential women's university. Dr. Mitra has joined this prestigious university in 2017 after serving as an assistant professor at NIIT University Department of Natural Sciences. In 2015, he has received his PhD in material sciences from IIT Bombay, and in 2006, he received his master's degree in condensed matter in physics from Banaras Hindu University. Functional materials such as piezoelectric and ferroelectrics, energy harvesting and storage using diverse synthesis techniques such as bulk ceramic thin films and ceramic polymer nanocomposite are among his research interests. Actuators, sensors, transducers, energy harvesters, flexible and variable electronics, and supercapacitors are among his other interests. He has completed and worked on various research projects with funding from DST, SERB, IIT UP, and the European Commission program. He has a number of journal papers in reputable journals in the field that includes Journal of Applied Physics, Scriptia Materialia, Journal of American Chemical Ceramic Society, RSC Advances, and others. And he has also won Indian patent in his name. Over the last few years, he has established a number of collaboration with academicians, scientists from National University of Singapore, Ulsan National Institute of Science and Technology, UNIST South Korea, A-Star Singapore, INUP IIT Bombay, BARC Mumbai, ARCI Hyderabad, CGCRI Kolkata, and NAL Bangalore. In his lab at Vanasthali Vidyapit, he is now mentoring 3 PhD scholars and several master students for their dissertation. In 2017, he received the SERB Government of India's Early Career Research Award, and he is a life member of the Material Research Society of India, Bangalore, MRSI Bangalore, and IIT Bombay Alumni Association. With these words, I would like to hand over the session to Dr. Supratim Mitra. Sir, over to you.
Thank you, Dr. Chaudhary. On behalf of MET 2022, first of all, I would like to welcome you in the first session of day 1. And I think the theme of this session is physics of materials and technology. So I guess we have 6 presentations in this session. So first, whose presentation will be first?
Ekta Jain is right now unavailable, sir. So maybe we have to cancel that presentation. Mohanavel, we are just trying to check his mic, but probably he is not audible. Mohanavel, are you there right now? Yeah,
yes, sir.
Yeah, it's working. So we'll start with Mohanavel, sir. Yeah.
Okay, so our first presenter will be B. Mohanavel, and I guess he will be presenting structural, optical, and morphological study of nanoscale cadmium oxide manganese thin film, which is prepared by chemical spray pyrolysis technique. So over to Mohanavel. Please continue.
Yes. Good noon to all. First of all, I give thanks to all those who give this opportunity to me. So I need to start. Before start, I will be sharing my PPTs. Yes, sir. You don't view this one? So shall I start?
Yeah, you can go ahead.
Okay. Thank you, sir. Thanks. So, the warm welcome for all. So, my topic is very interesting one. The structural, optical, and morphological studies of nanoscale cadmium oxide doping of manganese. The thin film prepared by chemical spray pyrolysis. This is the older one, and also very easier thing. We can be the even coating, we go for this spray pyrolysis. So our introduction, the spray pyrolysis, deposition of even any other material, any material, but material will be cadmium oxide and M, manganese thin films on. Class offers the possibility for large area deposition at relatively low cost. This is the main reason most of people are need to go approach for the spray pyrolysis method. So in this topic, in this explanation, what I need to explain is the optical properties of such films suitable for solar cell applications. So next one. So this is a small introduction about thin film. And thin film is a layer of material whose thickness varied from micrometer level to nanometers. So where there are the applications of thin films, nowadays it will be very more. I will be shortlist due to the lack of time durations. They are widely used for optics, electricity, computer, magnetics, and mostly nowadays need for another abundant fuel for others is solar. That's why it's a last one. So next thing, the materials and methods. So I already told the technique will be spray pyrolysis. So these are the basic, the substrate cleaning process. Soap water, distilled water, mushrooms are used for cleaning purpose of the glass plates. So what are the precursors where we have used is cadmium acetate and magnesium acetate. So various molarity ratios we have taken 0.05. It will be constant for cadmium. And the various manganese ratios are 0.001, 0.002, 0.003 molarity. The absolute temperature will be 250 degree. Even the 3 molarity concentration, the 0.002 give the more appropriate result compared to other two. Yes. So materials, methods. The cadmium oxide coated with magnesium thin films coated on glass substrate, 250 degree by spray pyrolysis technique. The precursors we are used is cadmium acetate plus manganese acetate. What are the characteristics? XRD, SEM, UVs. The structural studies of compare with the XRD. The morphology will be SEM. The optical properties are UVs and transmission spectra also used. So these are the thing. Why we are go for cadmium oxide? The main reason is one of the potentially useful N-type semiconductor material. So the most of people are use the word toxic. Due to that reason, we avoid the toxic materials. We go for more numbers. But even though it's a toxic, but it gives more results and also more widely useful for the transparency purpose. We are using cadmium. So it is high electrical conductivity and high optical transmittance in the visible region also. The cadmium oxide, the thin films are the great attention to semiconductor nature. The main reason is it is a crystal structure where rocks are come under the FCC, phase center QD. It is used in variety of applications such as already told, solar photothermal conversions, improve overall performance of TCO. Yes, it's nothing but a transparent conductive oxides. So these are the results, the XRD results. The XRD results are recorded in 2 theta range from 10 to 90 with the step of size will be 0.02 degrees centigrade. So it is indicating the polycrystalline FCC structure. The planes are indexed at 111 plane, 200 plane, 220 plane, and 222 plane. The volume of the precursor is increased. I already told it will be increased from 10 ml to 50 ml. The intensity of peaks are also increased. The orientation is changed from 111 to 20 for lower to higher concentration of Mn at the same temperature. But the temperature will be already mentioned. The optimum temperature to 250 degrees centigrade. The intensity of peak of plane 11 slightly shifted to 201. When it will be shifted is doping of manganese. So the concentration, the doping is increases. The intensity of peaks also increases. I already told 3 concentration we are used in this paper. But optimum is 0.002. That is a good shifted values. It gives the plane from 1 small changes, slightly shifted to Mn doping concentration. So the radius also difference from the Mn to the CDA will be 1.4 angstrom, CDA will be 1.48 angstrom. So this is the structure, the various concentration levels, precursor solutions, and it's all undoped is at the base, and doping a manganese small 0.001 those cases. Second will be 0.002, 0.3. For increase the precursor solution, I told the intensities also increases. So the next one, morphological studies will be using the results of SIM, scanning electron microscopy. The CDO, cadmium oxide, Mn deposit was grown as a spherical shape like marker. It's a spherical shape. It consists of closely packed, uniform spherical shape. The grains also arise without cracks. So these are found to be very high quality and good uniformity, high transmittance and good crystallinity also. The grain size and surface roughness of cadmium films are controlled by adding the doping of manganese. Whenever you increase the doping of manganese to a certain level, it also reduces the surface roughness also, and also controlled by the grain size, and also cracks reduces, also use this one. The grain size of pure cadmium film CDO is about 35 nanometer. If you dope, the grain size will be increased to 39 nanometer. Whenever the grain size will be increased, the cracks are reduced. They are very new. So these are the structures of SIM. Another two would be at down. So this is the next. Our thing will be grain size and strain analysis. The grain size of undoped film was found to be 43 to the range of 50 nanometer, but we are increasing the precursor 10 to 50 ml. For Mn doping for the range is changed from 38 to 54 nanometers. Increase in grain size, decrease the micro strain. I already told the grain size increased, the cracks also reduced the surface area. It will be happens only the doping of manganese. The grain size found to be increased as the precursor concentration increase. The maximum grain size and the minimum strain is attained at the higher concentration of doping of manganese 0.002. I already told this is a 3 doping, this is one get the optimum. So these are the concentration strains, the grain size and the strain curves. You see the 3 variation of precursors solution, but everything will be at the certain level. Whenever we are increasing the precursor solutions, the size will be increased, the strains also reduced. It will be come downwards. The optical properties. The film shows observation at 200 to 1200 nanometer. The thin films are light yellow but high transparency. The smooth increases the transmission from 550 nanometer to 900. Even though we can be film source absorption capacity will be 200 to 1200 nanometer, but the transmission will be very good in 550 to 900 nanometer. The transmitter decreased at high doping level. I already told the pi nano 2 is giving the good transmissions, but we increase the doping for 0.03. It also decrease the transmitter nature. That's why we can give the range from 200 to 1200 nanometers. It will have the low transmission in the IR region. It's like a metal-like structure. That's a mirror, the reflecting nature. The band gap we get is 2.5 EV to 2.6 EV. The refractive index undoped cadmium is 1.2509. Increase significantly higher concentration of Mn. The various doping levels. So these are the transmittance and absorption curves, closely doped and concentrated levels. The absorptions, the transmissions, the optical absorption curves of 0.5 cadmium. So these are the refractive index of CDU, undoped, how it will be reduced for in case of manganese dope levels. So finally, what we conclude this one is manganese dope CDO films are coated on glass substrate at 250 degrees centigrade by spray pyrolysis technique. The X-ray diffraction some transmission spectra, band gap are investigated. The XRD pattern confirms stereo phases with differential orientation along 1 slightly shifted to 200 for higher concentration. Specifically, the concentration level will be 0.001, not for 0.02. If we increase that concentration level by 0.03, the transmission also reduce because I already informed the transmission is good enough only for 50 nanometer to 100 nanometer. Finally, it has been concluded that the M2 residual films have improved properties and are good candidates for the photovoltaic applications. So in future, it will be available for CZTS, CAGS. So it will be improved to some things are some research are going for CTS and CZ are also going. That's why this is my area. Has a few reference. Also, thanks and thank you for all. Once again, thank you. Give me the opportunity to share my views. Thank you for all. Once again, thank you. If any questions, I will be able to answer.
Thank you, Mohanabal. Is there any questions from the audience? You may please ask. Okay, so I have one just suggestion
Yes, sir.
that
Yes.
if you have seen, you have arranged your slides in such a way that you are discussing before the actual graph is presented.
Yes, sir. Yes.
I mean, for example, if you see slide number 9,
Yes, sir.
can you go back to slide number 9?
The way, sir. Yes, sir.
Slide number 9.
Yes, sir.
Yeah. See, you are talking about the XRD
Yes, sir.
results, but
Yes, sir.
before you have not shown the XRD pattern before.
Graph. Okay, sir.
So what
I'll
usually
change
you should do, you put the graph slides which containing the graph first, and then you
Okay.
discuss what is the result. In every cases, like ACM also, you are talking about it is a spherical shape
Okay.
particles. So this you should keep in mind. Thank
Okay,
you.
sir. In future,
So-
I will be changing, sir. This is the first time I will be do this one. So these
Thank
are mistakes. Sorry, sir.
Okay. Fine. So okay. Again,
Okay.
thanks. Let us thanks again, Mohanabal,
Okay,
our speaker. Okay. Thank you, Mohanabal.
Thank you for your suggestion, sir. Thanks, sir. Thank you, sir.
Now, next participant will be Tara Prasad. Nidhi Jain is present. Is Nidhi Jain is present?
Yes, sir. Hello.
Yeah, Nidhi.
Yes, sir. Yes, sir. I'm present.
Nidhi. So our next presenter will be Nidhi Jain. Nidhi
Oh,
Jain. Let me tell you what he will be talking about. So she will be talking about synthesis and characterizations of nanocomposite polymer electrolytes dispersed with zinc oxide nanoparticle for electrochemical application. Over to Nidhi. Please, Nidhi, continue.
yes, sir. Good afternoon, everyone. Myself Nidhi. I'm here to present my topic on synthesis and characterization of nanocomposite polymer electrolytes dispersed with ZNO nanoparticles for electrochemical applications. I am from Dr. Harising Gaur University. Now, outlines of my work: introduction, objective, synthesis and characterization techniques, resultant discussions, conclusion. Now, introduction. As we all know that our conventional energy sources are limited in our amount, so we will search for renewable energy sources like rechargeable batteries for our daily needs like laptop battery, camera, smartphone batteries, and heavy electric vehicles, etc. So, for all these things like laptop, we will need electrolyte material, which so we are discussing on nanocomposite polymer electrolytes in solid form. When generally electrolytes are material with high ionic conductivity and low electrical and conductivity. Objective of my work to synthesize nanocomposite polymer electrolyte thin films which are thermally, chemically, mechanically, and is flexible in nature, and these are safe to use, and these are also light in weight, and these can be prepared by solution casting method, and all these film are characterized by XRD, FTIR, impedance spectroscopy for their electrical and structural analysis. Why we are working on magnesium based system? As we all know that work on lithium based electrolyte are large in amount, but working on lithium system in open environment is very dangerous. That's why we are choose to work on magnesium based system. uh, magnesium based uh, magnesium based electrolytes are low in cost because these are available in large amount in our environment, and also size of magnesium ion is nearly comparable with lithium ion. Now applications of nanocomposite polymer electrolytes. Our prepared nanocomposite polymer electrolyte can be used in rechargeable batteries, chemical sensors, fuel cells, solar cell, supercapacitor, etc. Now, preparation technique. We will prepare these nanocomposite polymer electrolyte by weighing of proper amount of polymer as host, ionic salt as a source of ion, and DMF as a solvent, and various type of nanoparticles. In our case, we will using ZNO nanoparticle. Firstly, we will weigh proper amount of polymer and ionic salt, and we will add DMF. Then we will stir this solution at room temperature for 24 hours. After that, homogeneous solution is obtained. After that, we will add ZNO nanoparticles. Then again stir for 24 hours. Then transfer this solution into petri dish. After that, we will dry that solution in oven to get our film. Now, we will characterize all these film by XRD, FTIR spectrophotometer, and impedance analyzer. Result and discussions. Firstly, structural analysis of this film gives that our electrolyte was confirmed. Electrolyte prepared was confirmed. This is the XRD pattern of our nanocomposite polymer electrolyte. From this figure, we will observe that peaks of dispersed nanoparticles are observed. This confirms complexation of electrolyte. And from by using this curve, we can also calculate its crystallite size by using Devasir's formula that is D is equal to K lambda by beta cos theta, where K is Sierra shape factor and beta full width half maxima of particular reflection peak, and lambda is wavelength of X-ray used. And this is this is a table for representing all nanocomposite polymer electrolytes crystallized size, and we will got minimum crystallized for our Option system, that is 78% of PVDF, 38% of magnesium nitrate, and 3% of ZNO nanoparticle. Now a structure FTIR analysis. From FTIR analysis, this will also confirm formation of complex, and this is the FTIR pattern of pure PVDF, pure magnesium nitrate, solid polymer, ZNO nanoparticle, and our Optium system, that is 38% of ZNO nanoparticle in solid polymer electrolyte. And this is the table for gives us some give information about peaks obtained in our pure PVDF. Now, ionic conductivity studies. This is our important study for nanocomposite polymer electrolyte to be used in electrochemical devices. We will we will form our composition, that is 100 minus x weight percent of PVDF, x weight percent of magnesium nitrate, where x is equal to 0, 10, 20, 30, and 40 and weight percent. And we will use the formula for ionic conductivity, that is L upon RB by A, where L is thickness of our polymer electrolyte film, is area, and RB is bulk resistance. Figure first represent complex plot for solid polymer electrolyte cells or for our composition. And insert shows typical equivalent circuit of cell with non-blocking electrode. And figure C can represent concentration dependence of our salt at room temperature. From figure second and first, we will got highest conductivity value for 30 weight percent of MgNO3 in poly- polyvinylidene fluoride. Now, this is the concentration dependence for our ZNO nanoparticles in solid polymer electrolyte system. That is our, so we will got optimum concentration for solid polymer electrolyte, that is 78% of PVDF and 38% of magnesium nitrate. We will assume this as phase 1 and ZNO nanoparticle as phase 2 for preparation of nanocomposite polymer electrolyte. On adding this nanoparticle in our solid polymer electrolyte, conductivity value got increasing, and for 3 weight percent of ZNO, we will got maximum conductivity, that is 0.87 into 10 to the power minus 4 Simon per 10 to the power minus 4 Simon per centimeter for 3 weight percent of solution at room temperature. Now, these are dielectric analysis, dielectric curves for our optimum system at room temp at different temperatures. In this figure, it is observed that as temperature of electrolyte increases, dielectric constant value got also increases. And second observation was, as frequency increases, dielectric constant value got get saturated at higher frequencies in both curves. Now, transport number measurement and discharge characteristic. Figure first represent current versus time plot. And from this curve, we will calculate transport number for our electrolyte system. And we will got the transport number for our systems, that is near in range of 0.96 to 0.99. And 0.99, which is close to 1, this represent our electrolyte is purely ionic in nature. And all transport number values are represented in table given below. And figure second represents the discharge plot, that is plotted between voltage and time. We will discharge our electrolyte by fabricating electrochemical cell in configuration as anode, electrolyte, and cathode. And we will calculate all cell parameters like current density, discharge time, discharge capacity, power density, and energy density. For our optimum system, we will got OCV value, that is 1.85 volt, and all the current density, that is 81.01 micrometer per centimeter square, and all these parameters are listed in our table. And we will got optimum value for our 78% of PVDF, 38% of magnesium nitrate, and 3 weight percent of ZNO system. This system our this system gives best results. Now, conclusion. In our work, we will synthesize a series of nanocomposite polymer electrolyte dispersed with ZNO nanoparticles to enhance its electrical conductivity, mechanical stability, and all these properties. And these films are prepared by solution casting method, and XID and FTI result confirm formation of complex composition and frequency dependent ionic conductivity studies gives our ionic conductivity. We will got highest value, that is 0.87 10 to power minus 4 Simon per centimeter at room temperature for our optimum system, that is 78% of PVDF, 38% of magnesium nitrate, and 3% of ZNO system. And for this system, transport number value is 0.99. And from discharge plot, we will got OCV value for our Optium system, that is 1.85 volt, with good energy and current density values references. And thank
Thank you, Nidhi. Is there any question from the audience? Is there any question for Nidhi from the audience?
No, sir.
What's
Okay.
the ion mobility in magnesium ion mobility in comparison to lithium? We have studied about that.
No, sir. No, I'm not studied about that.
Okay. Okay.
Is there any further question from the audience? Nidhi, I have one question. If you just
Yes.
go to the
Yes, sir.
preparation part where you have prepared the sample, can you
Yes,
go
sir.
to that? Can you go to that particular slide?
Yes, sir.
And I think one suggestion I should give you, put a slide number so that everybody, okay, you have put it.
Oh,
Okay. So now how do you confirm that the film you have prepared, it has a uniform thickness, and have you measured the thickness?
Yes, sir. I have measured the thickness by using micrometer screw gauge.
So what was
Yes, sir.
the
I have
thickness
measured
of
thickness.
what
So
was the thickness?
nearly micrometer 150 micrometer.
150 micrometer. And how do you confirm or make sure? How did you make sure that your film has a uniform thickness throughout, not different? Because usually, if you have not taken any other measures to make it completely flat, it is very difficult to get a uniform thickness film using a petri dish. So have you done anything for that?
No, sir. But when I prepared this film, मतलब जस्ट जैसे ही मतलब वो ड्राई हुई थी और हमने मतलब उसको उसको सेव करके रख लिए थे, तो वो
No,
यूनिफॉर्म थिकनेस ही मिला था। मतलब उसको टेम्परेचर हाई नहीं जाने दिया था कि मतलब उसका सेव वगैरह कुछ मतलब
any
डिस्टर्ब हो।
reason any reason why you have chosen PVDF
Yes, sir.
as
So
the polymer?
PVDF has high dielectric constant, and it has vinyl group present in that F atom present in vinyl group has capacity to attract a cation toward itself. So मतलब when we मतलब when complex was found, then मतलब पीवीडीएफ से मतलब उसका डायलेक्ट्रिक कांस्टेंट अच्छा है, तो उससे कंडक्टिविटी वैल्यूज भी अच्छी मिलती है, क्योंकि उसमें पिनाइल ग्रुप है और उस वो कैपेसिटी उसकी अच्छी होती है अट्रैक्ट करने की कैटायन को, तो वो कैटायन के साथ कॉम्प्लेक्स इजीली फॉर्म कर लेता है
And what is the purpose of
और उससे
using zinc
मैकेनिकल
oxide?
स्टेबिलिटी कैसा मैकेनिकल स्टेबिलिटी भी अच्छी मिलती है उससे,
Okay, got it.
स्टेबल फिल्म मतलब फॉर्म होती है।
Is there any reason for using zinc oxide?
Yes,
What
sir.
is the particular?
Jim, sir, I have described various types of nanoparticles like MgO, TiO2, Al2O3. I have studied with different particles, but with ZNO nanoparticle we will got highest value of conductivity.
Okay, thank you, Nidhi. So if there is no further question, let us thank Nidhi. Thank you, Nidhi.
Okay, sir.
Now, our next presenter is Tara Prasad. Do we have Tara Prasad? Okay, so if Tara Prasad is not available, may I ask Prayag Jyoti?
Yes, yes, I'm here.
Sorry, Parag Jyoti. Parag Jyoti,
Yes, sir.
can you please start? Yeah, please.
Yes, yes. Okay. Am I audible?
Yes, you are.
Yes, sir.
Okay. Thank you. Very good evening to all of you. And first of all, I would like to thank MET for giving me the opportunity to present my work. And today, actually, I'll talk about my research work on the topic morphological, thermal, and low temperature acid conductivity study of poly-3,4-ethylene dioxide hyphene. In the presentation, I will give a basic introduction about the conducting polymer. Then I will go for the to talk about the synthesis process of my system, that is PDOT and nanotubes. Then I will discuss about results, and then finally conclusion. So as you know that conducting polymers are generally insulating materials, but fortunately, three great scientists, Asa Higar, Alan G. McDermott, and H. Shirakawa, they have found that there are certain kind of polymers who shows the conductivity. And for that reason, they have been awarded Nobel Prize also in 2000. And the basic requirement to become a polymer conductive is that they must have alternates single and double bond. And the second requirement is that we need to do doping to make a conducting polymer conductive. So how we can achieve a conducting polymer, and how we can make a conducting polymer conduct electricity, that is a doping process is important. But the doping process in case of conducting polymers is somewhat different. If you talk about in semiconductor, if you talk that the dopant species occupies the position within the lattice of the host material, which results either electron rich or electron deficient sites without such transfer between the two sides. But if you talk about conducting polymers, this is some kind of redox reaction. That means electron may be removed from the cell or may be given to the system. So that's why the doping process in case of conducting polymers is somewhat different. And there are basically three types of such carriers. That means quasi such carriers are produced in case of conducting polymer. And depending upon the main situation is whether there is a degenerate energy is there or not. If there is a degenerate energy state, then generally solitons are formed. If we give an example, there's a tense polyacetylene. This is the example of conducting polymer having solitons such carriers. Then another case, if there is no degenerate such carrier, then at lower doping levels, polarons are formed, and if it goes on increasing the dopant concentration, then biopolarons are formed. So then we'll go different synthesis mechanism to synthesize different nanostructure. There are basically two major categories we can divide. One is a chemical polymerization technique, and another is electrochemical polymerization technique. And here we have followed the chemical polymerization technique, and we followed the self-assembly method. Although the synthesis of nanostructure by template synthesis method is very good, that means we can synthesize very well-ordered nanostructures. But there's a major drawback in case of template synthesis, that we need to remove the template after synthesis of the nanostructure. That's why there may be a chances of destruction of the nanostructure. That's why you have followed the self-assembly method. Here, the dopant, what we have used, they serve as a micelle, and that guided the formation of nanostructure. So that's why we have followed the self-assembly method in our case. So these are some application of conducting polymer nanostructure. We can say OLEDs use solar cells, electrochemical windows, capacitor, micros, and flexible display. These are some kinds of application of conducting polymers. And here there's a materials what I have chosen. In case of monomer, I have chosen 3,4-ethylene dioxide hyphene. Then I have taken FeCl3 as an oxidant to synthesize, and camphor-sulfonic acid in our case I have used as a dopant. And here this camphor-sulfonic acid from the micelle, and this actually guided the formation of nanostructure in our case. These are the solvents that I have used: aceton methanol, acetonitrile, and anhexane to remove the unwanted product from the synthesized nanostructures. So this is the block diagram of synthesis of PDOT nanotubes. So first of we have added E dot, that is monomer in anhexane, and then we have used add 1 molar millimolar of CSA, In another beaker, again, we have used the FeCl2 without add as FeCl2 in acetonitrile solution. Then after that, they are kept under stirring into different stir. Then we had drop wise that's FeCl3, that means oxidant solution in a step of 2 seconds. Then kept under stirring around 24 hours. And then finally, after 24 hours, we collect the product and we washed it and filtered it with first double distillation, then methanol, acetone, and finally we dried it for different characterization. Okay, so these are the HRTEM micrographs of our synthesis nanotubes. So from the 10 micrographs we have taken actually I have synthesized 4 different samples from 1 millimolar to 1 molar. So we have taken 10 micrograph of only 2 concentration, that is lowest and highest. So it is seen that it's 10 micrograph is confirmed the formation of very well ordered nanostructures, and we have also calculate the histogram, and from the histogram we plotted the histogram Gaussian plot fitting, and then there from the we've seen that in case of lower doped concentration, that means 1 millimolar cases, the average diameter of the nanotubes was found to be 65 nanometer, and if it goes on increasing the dopant concentration, then it's highest, that is 1 molar says dope cases, the average diameter was found to be 1 nanometer. Then we have also done the SED pattern, and the SED pattern shows the diffuse ring in case of both the samples, and which confirms that the semicrystalline nature, this is amorphous nature of the material, and the presence of spots, that means ring spots and white dots signify the semicrystalline nature of the material. That means we can say that the presence of both diffuse ring as well as the white spot suggests that it's a semicrystalline nature. And we have done XRD, and from XRD pattern we have seen that there is no sharp peaks has been observed, and this is we can say that it's a semi-crystalline materials. And from there we have calculated degree of crystallinity, and from we have seen that the value of K is found to be increased with increasing the dopant concentration. That means which is also we can say that at high dopant concentration we have observed very well ordered nanotube. That means the polymer chains are very well ordered if it goes on increasing the dopant concentration. And then we have done the micro-Raman analysis also. Micro-Raman spectra, all characteristics bands, vibration bands are observed, but especially one important point, we have seen that with increasing this dopant concentration, the C alpha, C beta is symmetric stretching, vibration stretching found to be a shift towards lower wave number region. So which is indicates there is a conjugation transformation from benzenoid to quinoid structure. So that means we know that the quinoid structure is more well ordered. So we can say that the formation of which is we can correlate with the XRD results and 10 micrograph. Then we have performed the thermogravimetric analysis to see the thermal stability of our synthesis sample. And here we've seen that all the sample cases up to near about 120 degrees Celsius, degradation was observed, and this may be due to the removal of water which is trapped inside the polymer chains. And then above 271 degrees Celsius, this may be due to the degradation of polymer backbones. And also we see that we have seen that for high concentration, the nanosamples, this samples shows the higher stability. And so we can say that it is a we can correlate with our XRD results. Then we have performed AC conductivity analysis. So AC conductivity analysis is for room temperature for all the samples, and one is for different temperature for highest of sample cases. And from there, we've seen that lower frequency region, it almost shows frequency independent characteristics. So which we can say this is the contribution of DC part, and the dispersive behavior at high frequency region it's corresponded to AC. And in order to understand the presence of transport mechanism in our system, we have fitted our highest DOP sample with a different temperature with this equation number 2. Then from there we have find out the value of S, and it is seen that the value of S found to be decrease with increasing the temperature. That means we perform from 80 Kelvin to 300 Kelvin. So this suggests that because it suggests the presence of transport mechanism in our cases is correlated virial Hoping model, because if you decreases with an increase of temperature, then we can say that the presence of correlated virial Hoping in our system. And then conclusion. So we can say that from the micrograph, we can say that we have successfully synthesized the well-ordered nanotubes by using CSA as a dopant, which acts as a soft template in our case. And the formation of nanotubes, average diameter is found to be 65 nanometer to 101 nanometer. And from XRD micrograph, XRD pattern, also we have seen the diffraction pattern. Also we have seen that the enhancement of crystallinity in our case for highs of sample. And in micrograph, at Raman spectra, also we have seen that there is a conformational transition from benzene to quinone structure. And thermographic plot also shows the enhancement of thermal stability with increasing the dopant concentration, which can be correlated with the XRD results. And then finally, with the help of acid conductivity analysis, we can say that the presence of the transport mechanism in our system is controlled by correlated Hopian model. So thank you.
Thank you, Parag Jyoti. Is there any questions from the audience? Anybody would like to ask anything to Parag Jyoti? Okay, Parag Jyoti, I have one small query. Can you
Okay, sir.
please go to slide number 13? Yeah.
Slide. Yeah, okay.
13. I think next slide.
13. Okay.
Yeah, so here, obviously, you said already that a prominent peak is not being observed,
Yes.
and you have calculated the the degree of crystallinity as 46%.
Yes. Yes.
That so, what is the is that the case of D? 46%.
Sorry.
Sample number T, one mole CSA
Yes,
concentration.
yeah, 1 molar sample. Yes, D.
Okay. So, how did you calculate the crystallinity?
Yeah, actually, we have taken the area, total area. We have count.
So you have fitted the curve with in origin first.
Yes, in origin. Yeah.
Okay, and
Then
then
we
you
calculate the total area.
okay. So you choose the whole scan area. And
For
then,
that, we have supposed that in our case the 3 small peaks are there.
Mhm.
So this we calculate the area of the 3 peaks. Then it's divided by total area of the whole diffraction pattern actually.
Okay. So I think
It's just a rough estimation. Yeah.
okay, now. Okay. Thank you, Parag Jyoti. If there is no further question from the audience, let us thanks again Parag Jyoti for his talk. Okay, thank you, Parag Jyoti. Now
Thank you.
our next speaker, I think Rajendra Kumar Dikshit. Can we have Rajendra Kumar Dikshit?
Yes, sir. I am here.
Yeah. So Rajendra
I'm
Kumar
audible, sir?
Dikshit. Yes, you are audible. So
Okay.
the title of the talk of Rajendra Kumar Dikshit is to investigate the electrical, optical, and dielectric properties of PVP with PVDF and PVA for optoelectronic device. So over to Rajendra Kumar.
Okay, sir. 1 minute. Sir, my screen is visible?
Yes, your screen is visible.
Yes, it's visible.
Okay, thank you, sir. to investigate the electrical and dielectric properties of PBP with blending PBDF and PBA, especially to investigations is regarding with the optoelectronic devices. I think something is, sir, isko,
There
1
is
minute.
there is little echo.
Okay. Okay. Now it's perfect, sir.
Yes, now you are audible properly.
Okay, thank you so much. And slide is visible. So this was the abstract which I have submitted earlier. Dr. Sandhya Patel is my research mentor, is also co-author of this investigation. My research objective of this paper is to analyze the structure and morphology of my prepared sample. Photoluminescence spectra analysis, especially emission and excitation spectra, is also analyzed here. And impedance spectroscopy for the electrical and dielectric studies, and thermal stability also studied by using the DSC data. And now I'm interested to use the PBP because it is a very attractive polymer material in a low molecular weight, especially in 10,000 molecular weight. And with this, I have just tried to use the PBDF and PBA, these two very important popular polymer material nowadays. PBDF is the semi-crystalline material, so it's definitely provide some very specific properties to enhance the strength of polymer, especially a PBP, because semi-crystalline materials provide the thermal stability, mechanical stability. These properties definitely enhanced by using the PBP and PBDF. So in between the process, synthesis process is the solution casting process. Here I have analyzed two samples. One sample is called S1. Here the 70% of PBP mixed with 30% of PBDF, and 30% of entire molecular weight percentage is used zinc sulfate. And in the sample 2, I just replaced PBDF by PBP with same ratio, and other ratio PBP and zinc sulfate is remained constant. So here the solvent was used commonly DMF, because the, all these materials are soluble in the DMF. So the solution casting method is used here. My prepared sample investigated by the structure analysis for XRD, morphology studied by FECM, field effect scan electron microscopy, and thermal stability also discussed here by the data on the basis of DSC and TGN. Photoluminescence spectroscopy gives some very important valuable results to me, which I show later on this presentation. And LCR meter is used for the electrical and dielectric analysis. XRD patterns show, in case of my left side, I use the sample S1 with the PBP and PBDF, and in the screen right side, a PBP PBA sample S2. Here the above green color XRD patterns show both of the samples showing 2 theta degree in 19.5. So in commonly, because the PBP is the dominant peak here and zinc sulfate is a common, PBDF is also near about the first peak of PBP. So it's a dominant peak of PBP is reflecting here, and both sample the 2 theta angle is showing 19.5 around. In that way, FECM, or it's commonly called the SEM data, images shows that the texture with PBP and PBA in the right side is a quite good texture in comparison to the PBDF with PBP. It means PBP and PBT blending is not quite good in comparison to the blending of PBP and PBP. So this images are really very important to show the morphology with PBP and PBDF and PBA. So it's a common, it's not a very good texture, but if comparatively, the texture of PBP and PBA is quite good in comparison to the PBP and PBDF. The thermal stability here discussed by the using of DSC and TGA data. In the right side, again, the sample S1, and it shows that because the PBDF has good thermal stability in comparison to the other polymer materials which I have used here. So that's why the PBP, which earlier saw the transition temperature around 57 to 65 degrees Celsius, it's increased by using the PBDF quite good, and it's moved around 100, more than 100 degrees Celsius. So the thermal stability definitely increases in comparison to the PBA. PBBA is not increased the thermal stability too much of PBP in comparison to the PBDF. So the nature is the semi-crystalline material is definitely useful to enhance the thermal stability property. And similarly, the TGA data, which shows the weight loss with increasing the temperature, it's also increases in case of PBDF. Again, the reason is the semi-crystalline nature is very dominant nature. So it's definitely play the role. Now I come to the my data part where I put the frequency versus resistance. It's data collected by the LCR meter, or it's called the impedance spectroscopy. Right side, the sample S1 is showing that as we increasing the frequency, resistance is decreasing. And the data is come in the log form, so up to the 6.2 in the log frequency, it again increase, but in case of PBA, it's remain decreasing till that frequency, because here I have used the 20 megahertz highest frequency. If I use more than 20 megahertz frequency, it may be possible in the sample S2, it may be possible it's increase again, because I was not that kind of facility. So limited facility shows that up to the 20 megahertz frequency, a particular point with the PBDF, the decreasing of resistance get again increasing, but in case of PBA, it is remaining decreasing. This data again analyzed up to the 20 megahertz frequency and conductivity, which earlier in case of resistance it was happening here again. In the low frequency range, both samples showing the quite disagreement, but in the high frequency range and especially in mid frequency range, both samples are showing the similar nature. It's a conductivity increasing with increasing the frequency, but especially in case of low frequency, it's showing the disagreement. In difference is numerically is calculated, but I have not put it here. But it shows that in the low frequency, the vibrational spectroscopy plays the role in comparison to the high frequency. The all molecules, especially in PBP, nitrogen play the important role. In the PBDF, the fluorine play the important role. So these molecular weight is definitely play a very interesting role when we using the frequency, or when we using the vibrational frequency here. This was a very interesting result to me. On the basis of that, I have said that my data or my material is applicable for the optoelectronic devices, because I have read in the literature and I have found so many good research papers where the people say that if step-up function is showing by some polymer material, so those kind of materials are popular to use the optoelectronic devices, especially the photodiode, photodetectors, or for LED, or for some laser also here. So in case again the sample with using the PBDF, it's showing the little bit high value of the step-up function in comparison to the PBA. And the step-up function shows some transition when we use the AC voltage around 0.98 and 0.998 voltage. Both samples showing the transition shifting in the different manner. It's steps quite similar, quite states. So due to the stair, or due to steps, it is called the step-up function. It's really very useful for the optoelectronic devices. So it's an interesting feature, it's interesting data to me to show all of you. Dielectric permittivity is also very important to when we say these materials are useful for the energy storage devices or supercapacitor or like that. So here the frequency again up to the 20 megahertz. The both frequency, both samples showing the good agreement in the low frequency range. I have analyzed data from 1000 to 20 mega 100 frequency range. So in high frequency range, both samples showing the little bit disagreement. But in case of PBA, its dielectric permittivity showing the good result in comparison to the PVDF. So here I may say that PBA with PBP, PBP with PBA showing the good results for the dielectric analysis or for the dielectric purposes. This again I repeated that because photoluminescence studies has not performed with PBP, PBA, PBDF. Here I only analyze the data of PBP with using the zinc sulfate. Due to some limitations, that's why PBDF and PBA has not used here. But I have prepared 5 samples with different bit percentage. 0 to 100 weight percentage, and it varies up to 50 percentage. So it's very interesting data with the photoluminescence excitation spectra of the PVP. And here I found that the if we need to use a specific excitation value. So previously we was not aware that which value I should to use for the excitation of my sample. So during my some mathematical modeling, I found that on the basis of this peak analysis, here I use the mathematical modeling by using the Origin software. I analyzed the these spectra, excitation spectra, its peak value of excitation wavelength with its intensity counts, again put it here, and on the basis of that, this is a very interesting phenomena happen, or these are very interesting calculation found that here 460 nanometer and 450 nanometer, these two dominant excitations value can be used for making the excitations to find the emission spectra specifically. But I was also interested to excitation in under the UV light, because UV light, if we excite with the UV light, then purpose of my research goes to little bit high. This energy band calculations on the basis again on the excitation energy data I analyzed by some mathematical modeling by using the very fundamental theoretical calculations. On the basis of that, I found that as we vary the excitations value, the energy band gap shifted. Or on the basis of that, I was interested to say that the band gap tuning is possible with PVP under the different excitation. If we need to, because 4.04 electron volt, it's reduced 3.9 electron volt. So it's a marginal good variation of energy band gap. On the basis of that, I have read in the so many literature that if we found the energy band gap in between these ranges, then these kind of materials can be useful for the LED optoelectronic devices, or it can also play the very important metastable development of the laser or laser diodes. So these mathematical calculation or these mathematical analysis again give me some very valuable information to regarding the band gap tuning. Now these are the only 270 nanometer excitation spectra, emission spectra, sorry. I have excited under the UV region, and all samples, prepared samples showed the different emission spectra. Again, I analyzed this tip-to-tip data. Tip-to-tip data, it means I have found the peak-to-peak emission wavelength and counts. I analyze again the basic fundamental mathematical modeling. There, here I have two excitation value. One is a 270 nanometer excitation value, or in this case, I have a through 95 nanometer excitation value. It means these two excitation value under the UV region. So On the basis of that data, I again analyzed by using some basic mathematical modeling or using the Origin software. Here I found that if we excite my sample with 270 nanometer, here are the three peaks showing specifically. It means in that particular range, when we excited the sample by 270 nanometer, there are three sub centers are possible to there to emit the different energy or to emit the different wavelengths. It means again I'm able to say that the tuning is again is possible due to variation of band gap. It is again possible to the different but dominant peak is coming around 467 nanometer, but in that way two other peaks are also available in that graph, so it is again possible to tuning the bands. But when we excite Y395 nanometer, surprisingly here I found only one peak, and that peak comes 467 nanometer. So it means sir 5 मिनट की और so it means we can put our analysis on the basis of different excitations value. In case of 270 nanometer, I found three sub centers. In case of 395, I found only one dominant peak, that is on 467 nanometer. So on the basis of this entire discussion, I am able to say the PBP material using with the two blending with PBDF and PBA. So step up function shows that materials is possibly useful to develop the optoelectronic devices. And on the basis of my photoluminescence spectra analysis, again I found that the zinc ion play a very important role, because zinc is naturally a good photoluminescence useful ion. And the PBP is showing the three different subcenters, and band gap tuning is also possible there. So on the basis of this entire discussion, I am able to say that my material or my prepared sample is possible to develop the photoelectronic devices. I have not fabricated till now any device, but on the basis of only analysis, I propose this material for the photoluminescence devices. Thank you so much, sir.
Thank you, Rajendra Kumar Dikshit. Is there any question from the audience? Anybody would like to ask anything to the speaker? So I have a very small query. Why in your somewhere you have seen you have shown that the excitation spectra, right?
Yes, sir.
So and you have some experimental data.
Excitation curve. Are you interested to see?
Yeah. Can you please go to that particular slide?
Okay.
Yes, that one, 15, I guess. Yeah. And so this
Yes,
is your experimental data, right?
Yes, sir. These are the experimental data.
And the next slide, you have done some modeling.
Yeah, on the basis of this data, I done modeling this one.
So why don't you put these two data together to show that how the experimental data and the modeling matches? Because ultimately, when you are ultimately putting these two data into separate slides or separate graph, it is very difficult that how your mathematical modeling is matching with the experimental data. So that is my suggestion.
Okay.
Or if you have any explanation for that.
Okay, sir, the mathematical modeling only showing specific peaks. So I'm able to say that if we use these two excitations, then the emission spectra definitely shifted little bit towards to the blue shifting, because I'm not 100% say it's shifting, because I have not analyzed till this moment, but shifting is also showing in my research. Those data I have not prepared here to show, but mathematical calculation only provides some information or some specific information to me to say my experimental analysis is quite good, or not, I'm say to quite good, but it provides some additional information to say these excitations are valuable to us.
And the previous slide of this particular slide number 14.
This one, sir?
Yes, yes.
Okay, sir. This one.
Synthesis. Are you and
Okay,
Nidhi
sir.
are doing in the same lab? You and Nidhi are working in the same lab?
Actually, we are the same. We have using same lab. I'm also belonging to Saga University, and she's also
Okay.
there.
But so the thing is, correct me if I'm wrong. I think the same synthesis graph or photograph is shown by Nidhi also. That's why I asked the question in that particular set.
Syn-
So wherever
actually, my synthesis graph is similar. Graph means photo is the similar, because we have adopted same synthesis process,
No.
solution casting process. But see, yes, some
it's
other
not
things is,
it's not similar, it is the same thing, same photograph you have used. So you should be very careful when you are putting the same graph in the same session. You are putting two students of the same lab and putting the same. That is not the right thing to do, I believe.
okay.
So make sure, see this, it is a kind
But
of
these photos I have taken from
internet.
some internet which is not under the copyright, so you just download it from there. But the process was similar. That
Yeah, I understand.
it is not
You can put a,
real.
it's better to put a schematic instead of putting the actual image. So anyway, it is just
Okay.
a suggestion. Okay, thank you, Rajendra Kumar Dixit. So if there is no
Oh,
further
thank you,
question
sir.
from the
Thank you.
audience, let us thank Rajendra Kumar Dixit again. Okay, thank you. So our next participant is Ekta Jain. Ekta Jain is available? No. So Ekta Jain and Tara Prasad. No. Okay. So finally, we will invite our last speaker, Uttam Paliwal. Uttam, are you there?
Yes, sir.
Yeah, please continue.
Okay, sir. I am sharing my screen. Sir, is the screen visible?
Yes, Uttam,
Okay. Thank you for presenters for giving me a chance to present my research work in the prestigious conference. Good afternoon, everyone. Myself, Dr. Uttam Paliwal from Jain Narayan Vyas University, Jodhpur. And today I am presenting my work on structural electronic elastic electronic properties of the PE 0.75 Zn 0.25 as semiconducting alloy. I have done this work using first principles theory of density functional theory based calculations. The second six semiconductors and their ternary and quaternary alloys have a wide range of application in various optoelectronic devices like light emitting diodes, light sensor, photosensor, photodiodes, and they operate in a blue-green region. Beryllium and Zn are, as we know, that second group elements, and sulfur is sixth group element. So they jointly combinedly make second six semiconductors, and the important property is that they have wide band gap. Then third five materials like indium nitride, gallium nitride, and indium arsenate, etc. So we can alter their band gap and other properties like elastic strength and mechanical properties by combining beryllium based semiconductors and Zn based semiconductor. So this kind of structure is known as ternary or quaternary semiconducting alloys. Basically, these are not alloys like metallic alloys. These are ordered structures, and we can say that this is a mixing of semiconducting materials, and a new semiconducting materials is formed by mixing of two different kind of semiconductors. So in this work, we calculated the structural, elastic, and electronic properties of this alloy, in which we have taken 1/4 concentration of beryllium and one 3/4 concentration of beryllium and 1/4 concentration of ZnS. So we will call this material as BE 0.75 Z and 0.25 S semiconducting alloy. In this study, we calculated the lattice parameters, bulk modulus, elastic constants, and electronic band structure of the material. So the structure, we can see that this is a zinc blende type structure, which is basically a face-centered cubic structure, and ZnS and BES, beryllium sulfide and Zn sulfide, both have both semiconducting materials have this structure. This is each sulfur atom is tetrahedrally bonded by beryllium and Zn. So we can see that there are three beryllium atoms, because each of phase atom in the middle phase share 2 unit cells. So we can say that there are 1 Zn atom and 3 beryllium atom and 4 sulfur atom. And the Vico positions of beryllium, Zn and S are 3C1 and 4E. So this is a basic luteinide type structure which belongs to cubic space group, and its space group number is 215. We computed all the properties using quantum espresso package, which is a very famous and freely available open source package that calculates the electronic and structural properties of materials and solids and thin films using SCF calculation, and it takes pseudo potential basis sets for the calculation. In this study, we take the ultrasoft type of pseudo potential. The ultrasoft kind of pseudo potential are the pseudo potential which neglect the core electrons. Like for sulfur, there are only 4 valence electrons are taken in calculation, and the remaining 4 electrons like 1s, 2s are neglected. So and to incorporate the exchange and correlation functional in density functional theory, we used generalized gradient type approximation proposed by Purdue, Burke, and Azeroff, and the local density approximation type functional proposed by Purdue and Junger. So we basically took 2 different kind of functional. One is GGA and another is LDA. In the plane wave calculation, the energy cutoff of 50 Rydberg are taken, and charge density cutoff of 400 Rydberg is taken. And and the K point mesh of 9 into 9 into 9 is taken, considering the Monk-Horst page scheme of K point sampling. So we come to results, and first we discuss the structural properties. So when we vary the unit cell volume, this is a cubic structure, so only there is only one lattice parameter that can be varied, and which is lattice constant A. So by changing the value of lattice constant, we change the volume, and we calculated the total energy as different value of volumes. So we can the computed total energy versus volume curves are shown in this figure, and we can see that when we the curve corresponding to GGA type calculation has lower energy than the LDA type of calculation. So generalized gradient approximation type functional predict lower energy than the local density approximation. The computed energy versus volume data are again fitted to Murnaghan equation of the state, and by this we can calculate the total energy, bulk modulus, etc., and various other properties. So the computed properties are shown in this table, and we can find that lattice constant obtained by GGA is higher than LDA, and consequently the bulk modulus and elastic constants calculated using LDA is higher than GGA type of calculation. This is the trend of GGA calculations that they overestimate the lattice constant. This is a hypothetical system, so we cannot find any experimental data for this. So we compared our results with other theoretical calculations which are performed earlier by other workers using plane wave pseudo potential method, full potential linear augmented plane wave method, and full potential linearized muffin tin orbital method. And we can see that when we compare our results with other calculations, then we find our results using GGA close to FP-LFAW type calculation. Here we can see that our calculations show a lattice constant 5.08, where FP-LFW is near and it is 5.06. Also, the bulk modulus is achieved for GPA gigapascal, and this calculation also predict 86 GPA. Now we also computed the elastic constants for the system, and we only find one study earlierly performed for this system, and we can compare our results with the earlier study, and we see that our calculated values of elastic constant using LDA type calculations for C11 and C12 are near the PWPP method calculation, while our GGA value of C44 and shear modulus is near to PWPP calculation. Now we come to electronic properties, and we computed the electronic band structure for the system. We can see that valence bands are divided into two regions. One is around -10 to -15 electron volt, where the Fermi level is shifted to 0. We can see that here. And upper valence bands are from Fermi level to -7 for -7 electron volt. The first feature, we can see that both the conduction band minima and valence band maxima are at the gamma point. So our calculation predicted this is the direct band gap semiconductor, and when we talk about the band gaps calculated at other points, then we can see that at gamma to gamma there is band gap of 3.21 by GGA calculation, and by LDA calculation we obtained band gap value of 2.86. So GGA predict larger band gap than LDA calculation. And for other point like gamma to x point of symmetry, it is the x point. We find the higher value of gap. So this is the direct band gap semiconductor. The lower valence bandwidth is 1.72 using GGA, and using LDA we obtained 1.91. The upper valence bandwidth of GGA is 6.33 electron volt, and LDA we obtained the value of 6.73 electron volt. So we can also compare our results with other calculation, and we see that PWPP calculation also predicts the band gap of 3.20 electron volt, and similarly 3.19 by FP-LFW calculation. But FP-LMTO calculation predict band gap of 2.94 electron volt. So our results deviate from FP-LMTO calculation, but with FP-LFW calculation and PWPP calculations are gives also similar result to our calculations. So in this work, the density functional theory based calculation of structural electronic and optical properties, structural electronic and elastic properties are performed for this system, in which we modeled the PE 0.75 Zn 0.25 as ternary semiconducting alloy composed of 3/4 fraction of beryllium sulfide and 1/4 fraction of Zn sulfide. Our studies show that PBGGA give larger value of lattice constant than LDA calculation, and consequently the LDA predicts larger value of bulk modulus, elastic constant, and shear modulus than GGA calculation. The band structure calculation show that this structure is a direct band gap material, and band gap predicted by GGA calculation is more than LDA. In absence of any experimental results, we compared our results with other theoretical calculations, and we found that our results are in analogy of previous calculation. Thank you.
Thank you, Dr. Paliwal.
Yes, sir.
Is there any question from the audience? Okay, so Dr. Paliwal, what software you have used for this kind of calculation?
The quantum espresso package.
Okay. Is there any question from the audience? No. Okay. So if there is no question from the audience, let us thank again Dr. Paliwal for his talk.
Yes, sir. Welcome.
Okay. So I think we have no more presenter today. So thank you for joining this session. Now over to Dr. Chaudhary.
Thank you so much for your support, sir. It has been a fruitful session and we have ended on time. I guess there were two presenters who are not present for the presentation. So we had the presentations done on time and I'm very thankful to Supratim sir. Let's all thank sir for being with us and chairing the session. So as I've said, you can just mail me the evaluation sheet and
Sure,
then.
I'll do that. I'll do it.
Sure, sir.
Okay, thank you very much.
Thank you
Chaudhary.
so much, sir. So I'd like to wish everyone a happy learning session. I hope all of us join for the next session tomorrow morning. We'll send you the session details by email. Thank you so much. I'd ask the admin to end the session, please.